Venus rotates backward, not metaphorically, not as a quirk of how we define directions. In the most literal physical sense, if you watched Venus from above its north pole, you would see it rotating clockwise. Every other planet in the solar system, except Uranus, rotates counterclockwise from this perspective. The Sun rotates counterclockwise. Most moons rotate counterclockwise. The entire solar system has a preferred rotational direction inherited from the angular momentum of the rotating gas cloud that collapsed to form it 4.6 billion years ago. Venus rotates the other way. And that is not even the strangest part. Venus also rotates extraordinarily slowly, so slowly that a Venusian day is longer than a Venusian year. Venus completes one full rotation on its axis in approximately 243 Earth days. Venus completes one full orbit around the Sun in approximately 225 Earth days. The day is longer than the year. If you stood on the surface of Venus and watched the sky, which you could not because the atmosphere would kill you in multiple ways simultaneously, you would see the Sun rise in the west, move slowly across the sky, and set in the east. Approximately 116 Earth days after it rose. Then it would be night for another 116 days before the Sun rose in the west again. The combination of these two facts, retrograde rotation and extremely slow rotation, makes Venus the most rotationally unusual planet in the solar system. Uranus is technically also rotating in an unusual way. Its axis is tilted approximately 98 degrees from the perpendicular to its orbit, meaning it is essentially rotating on its side. But Uranus at least rotates at a more normal speed. Venus is both backward and almost completely stopped compared to the other planets. This is not a coincidence. Something happened to Venus. Something that fundamentally altered its rotation from whatever it was when the planet first formed. Something that happened long enough ago that its effects have shaped everything about Venus, its current geology, its current climate, possibly even the specific way its hellish atmosphere circulates. And understanding what that something was requires understanding both the physics of how planets acquire their rotation in the first place, and what specific events or processes can fundamentally reverse or slow that rotation over billions of years. Tonight, we are going to examine this question in full, not with a quick answer. The quick answers exist and are physically plausible, but leave most of the interesting science unsaid. But with a complete examination of what we know about Venusian rotation, what the competing hypotheses are, what evidence distinguishes them, and what the rotation of Venus tells us about the early history of the solar system, and about how catastrophic events can permanently alter the character of a world. Before we begin, if you put this on because the night is long and you need something to settle into, stay. The story of why Venus spins backward is stranger and more violent than most people know. Let us start with the most fundamental question. How did any planet acquire its rotation in the first place? Because understanding the origin of normal planetary rotation is essential for understanding why Venus's rotation is so abnormal. The solar system formed approximately 4.6 billion years ago from a rotating cloud of gas and dust, a molecular cloud that began to collapse under its own gravity. As the cloud collapsed, angular momentum was conserved. The specific combination of angular momentum in the initial cloud, determined by the turbulent velocities of gas molecules in the interstellar medium, established a preferred rotational direction for the entire collapsing system. As the cloud collapsed, it flattened into a disk, a protoplanetary disk, with the proto-Sun forming at the center and the disk extending outward. The flattening occurs because angular momentum prevents collapse in the plane of rotation. Material can fall toward the center along the rotation axis, but centrifugal force resists inward collapse perpendicular to the axis. The result is the characteristic flat disk structure of a forming solar system. Planets formed within this disk through a process called accretion, small particles colliding and sticking together, growing from dust grains to pebbles to rocks to planetesimals to protoplanets over millions of years. The specific angular momentum of a forming planet, the rotation it acquires as it grows, depends on the asymmetry in the accretion process. Material raining onto the growing planet from different directions carries different amounts of angular momentum, and the net angular momentum of all the accreted material determines the planet's initial rotation. The dominant effect is that planets forming in a prograde disk, rotating in the same direction as the disk itself, tend to acquire prograde rotation. The material in the inner disk orbits faster than the material in the outer disk, and when a forming planet accretes material from both its inner and outer sides, the asymmetry in orbital velocity produces a net angular momentum in the prograde direction. This is why most planets in the solar system rotate in the same direction as they orbit the Sun. But this prograde preference is not absolute. During the late stages of planetary formation, the largest accretion events, the giant impacts between planetary embryos that built the final planets from their constituent protoplanets, can dramatically alter a planet's rotation. A giant impact is not a gentle rain of small particles arriving from all directions. It is a single, massive collision that can deliver or remove enormous amounts of angular momentum in a single event. The spin of the final planet is strongly influenced by the geometry and size of the last major impacts it experienced. This is exactly what is believed to have happened to Earth. The Moon is thought to have formed when a Mars-sized body called Theia struck the proto-Earth in a glancing blow approximately 4.5 billion years ago. This impact gave the Earth-Moon system its current angular momentum, and Earth its current rotation rate of approximately 24 hours per day, while ejecting material that eventually coalesced into the Moon. Had Theia struck from a different angle, or at a different velocity, or with a different mass, the Earth might be rotating very differently today. The same type of catastrophic giant impact is the first and most natural explanation for why Venus rotates the way it does. If Venus experienced a giant impact late in its formation, after most of its accretion was complete, after it had acquired a prograde rotation from the general accretion process, a sufficiently massive impactor arriving from the right direction could have reversed the rotation entirely. Let us examine this hypothesis in detail. The giant impact explanation for Venus's retrograde rotation, because it is the most physically straightforward explanation and the one that most planetary scientists consider most plausible, while also acknowledging that it has specific difficulties. A giant impact on Venus capable of reversing its rotation would have needed to be enormous. Venus has a mass of approximately 4.87 times 10 to the 24 kilograms, about 81% of Earth's mass. Its current rotation rate, 243 days per rotation, corresponds to an extremely small angular momentum. Paradoxically, reversing a slow rotation requires less angular momentum change than reversing a fast rotation. But the rotation still needs to be stopped and reversed, which requires a significant impactor. Numerical simulations of giant impacts on Venus mass bodies, performed by several research groups over the past 2 decades, show that impactors containing approximately 1 to 3% of Venus's mass, arriving at oblique angles, are capable of reversing retrograde rotation under some initial conditions. For reference, the moon-forming impactor that struck Earth is estimated to have had a mass of approximately 10% of Earth's mass, larger than what is needed to reverse Venus's rotation. The specific geometry matters enormously. A head-on impact delivers angular momentum along the impactor's direction of travel. If the impactor is moving retrograde when it hits, this can significantly reduce or reverse a prograde rotation. A glancing blow from the retrograde direction delivers more angular momentum per unit impactor mass than a head-on collision, because the lever arm is larger. The specific combination of impactor mass, velocity, and angle determines whether the outcome is a reversal, a slowdown, or no significant change. Giant impacts of the required scale were common in the late heavy bombardment period, the period from approximately 4.1 to 3.8 billion years ago, when the inner solar system experienced an elevated rate of large impacts. The Nice model and subsequent dynamical models of solar system evolution predict that the final assembly of the terrestrial planets involved numerous giant impacts between planetary embryos. Most of these impacts occurred within the first few hundred million years of solar system history, and Venus's retrograde rotation, if impact caused, would have been established during this period. The challenge for the pure giant impact hypothesis is the extremely slow rotation. A giant impact capable of reversing Venus's rotation would typically produce a final rotation rate that is still rapid by Venusian standards, perhaps a few tens of hours per Venusian day, rather than the 243 Earth days observed today. To get from a post-impact rotation rate of tens of hours to the current 243 days requires additional processes acting over billions of years to slow the rotation further. This is where atmospheric tides enter the story, and they are one of the most physically fascinating aspects of the Venusian rotation problem. Venus has an extraordinarily massive atmosphere. Surface pressure on Venus is approximately 92 times the surface pressure on Earth, equivalent to the pressure at approximately 900 meters depth in Earth's oceans. The atmosphere is composed of approximately 96.5% carbon dioxide and 3.5% nitrogen. The total mass of Venus's atmosphere is approximately 100 times greater than the total mass of Earth's atmosphere. This massive atmosphere is not rotationally neutral. It interacts with the planet's solid interior through gravitational tidal forces. Just as the Moon raises tides in Earth's oceans, the Sun raises tides in Venus's atmosphere. These atmospheric tides produce a torque on Venus's solid body that affects its rotation. Solar gravitational tides on a planet's solid body, the same process that has tidally locked the Moon to Earth and that is slowly slowing Earth's rotation, produce a torque that tends to slow planetary rotation and align the rotation axis perpendicular to the orbital plane. For Venus, the solar tidal torque would slow its rotation and eventually produce a tidally locked state where the same face of Venus permanently faces the Sun. But Venus is not tidally locked to the Sun. Its 243-day rotation is not equal to its 225-day orbital period. If solar tidal torques were the only influence on Venusian rotation, it would be tidally locked. Something is preventing this. The atmospheric thermal tide is the additional factor. Sunlight heats Venus's atmosphere unevenly, more heating on the sunlit side than the dark side. This differential heating produces a pressure wave, a thermal tide, that travels around the planet with the apparent motion of the Sun in the Venusian sky. This atmospheric pressure wave exerts a gravitational torque on Venus's solid body, but crucially in the opposite direction from the solid body tidal torque. The competition between the solid body tidal torque, trying to slow Venus to tidal lock, and the atmospheric thermal tide torque, acting in the opposite direction and potentially driving the rotation, is what determines the equilibrium rotation rate of Venus. In 1964, the atmospheric tide hypothesis was proposed by astronomers studying Venus's unexpectedly slow rotation. The prediction was that if the atmospheric thermal tide torque is strong enough to balance the solid body tidal torque, the planet would reach an equilibrium rotation that is neither tidally locked nor rapidly spinning, but something intermediate. Venus's current 243-day retrograde rotation has been interpreted by some researchers as exactly this equilibrium, the stable configuration where the two competing torques balance each other. This interpretation, that Venus's slow retrograde rotation is not the result of an impact that reversed a fast prograde rotation, but rather the equilibrium state of a tidal atmospheric system, is one of the two main competing hypotheses for Venus's current rotation. The two hypotheses are not mutually exclusive. The most complete picture may involve both: an early giant impact that established retrograde rotation, followed by billions of years of tidal and atmospheric evolution that shaped the specific current values of the rotation rate and axis orientation. Let us examine the evidence and constraints that distinguish between these possibilities. The most direct constraint on the current rotation state of Venus comes from radar observations, specifically from the observations of Venus's solid surface through its thick clouds, using radar from Earth-based observatories and from spacecraft. Venus cannot be observed optically at the surface because the atmosphere is permanently cloud-covered, but radar penetrates the cloud deck and reflects from the solid surface. The first precise measurement of Venus's rotation period came from radar observations in the 1960s. The initial measurements suggested a rotation period of approximately 250 days, later refined to the current value of 243.0185 Earth days. The retrograde sense of the rotation was confirmed by the direction of the Doppler shift. The approaching limb of the planet shifted toward shorter wavelengths and the receding limb toward longer wavelengths in the opposite direction from what prograde rotation would produce. More recently, Earth-based radar observations and the Magellan spacecraft, which orbited Venus and used synthetic aperture radar to map its surface in detail from 1990 to 1994, have refined the rotation measurement significantly. By tracking specific surface features across multiple observing opportunities, the rotation period has been determined to approximately 243.0185 Earth days. One of the specific observational findings relevant to the rotation hypothesis debate is that Venus's rotation rate appears to change slightly over time. Measurements made by the Venus Express spacecraft from 2006 to 2014 found that surface features had shifted position relative to the Magellan mapping by approximately 13 kilometers, equivalent to a change in rotation period of approximately 6.5 minutes over a period of 16 years. This is a surprisingly large change for a solid planetary body. The apparent change in rotation rate could have several explanations. It could reflect exchange of angular momentum between the solid planet and the atmosphere. If the atmospheric circulation changes, it will exchange angular momentum with the solid body, and the solid body's rotation rate will change in response. This is analogous to how atmospheric circulation changes on Earth produce measurable changes in the length of the day, typically at the millisecond level for Earth, but potentially larger for Venus, given its much more massive atmosphere. The 6.5-minute discrepancy observed by Venus Express could reflect a seasonal or longer period cycle in the atmospheric angular momentum budget. Alternatively, the apparent rotation rate change could reflect errors in the models used to interpret the radar measurements. The mapping from radar observations to a rotation rate requires models of the atmosphere and surface that have specific uncertainties. Different groups have analysed the Venus Express and Magellan data and obtained somewhat different results. The ongoing Venus missions, Veritas and Envision, planned for launch in the late 2020s and early 2030s respectively, will measure Venus's rotation with much higher precision using radar and radio tracking. These measurements will determine whether the apparent rotation rate change is real, quantify its magnitude, and allow the exchange of angular momentum between the atmosphere and solid planet to be characterized in detail. Let us now talk about what the interior of Venus looks like and how the interior structure constrains the rotation hypotheses. Venus has essentially the same size and mass as Earth. It is often called Earth's twin. Its bulk density is approximately the same as Earth's. Based on these similarities, we expect Venus to have a similar internal structure: an iron-rich core, a rocky silicate mantle, and a silicate crust. But the specifics of the interior, the size of the core, whether it is solid or liquid, the temperature structure of the mantle, are much less well characterized for Venus than for Earth. The main reason is that Venus has no detected magnetic field of significance. Earth's magnetic field is generated by convection in its liquid iron outer core, the geodynamo. Venus has essentially no global magnetic field. This could mean Venus's core is entirely solid, no liquid layer to generate a dynamo, or that the core is liquid but convection is insufficient for dynamo action, or that the core has some other structure that prevents field generation. The absence of a magnetic field has implications for the rotation hypotheses. If Venus's core is entirely solid, cooled and solidified over billions of years, the coupling between the core and the mantle is through solid-state processes that are different from the liquid coupling in Earth. The core-mantle coupling affects how angular momentum is distributed between the core and the mantle, and whether the core and mantle rotate at the same rate or at slightly different rates. The Envision and Veritas missions will include measurements specifically designed to constrain Venus's interior, particularly measurements of the tidal deformation of Venus by the Sun's gravity, which depends sensitively on the size and state of the core. These measurements will significantly improve our understanding of Venus's interior structure and will constrain the models of how the planet's rotation has evolved over time. Let us now talk about the atmospheric superrotation of Venus, because this is one of the most striking features of Venusian climate, and it is connected to the rotation problem in ways that are not immediately obvious. Venus's atmosphere rotates much faster than the solid planet. The upper atmosphere, at cloud-top altitudes of approximately 65 to 70 kilometers, rotates with a period of approximately 4 Earth days. The atmosphere completes one rotation in 4 days, while the solid planet completes one rotation in 243 days. The atmosphere is rotating approximately 60 times faster than the surface beneath it. This atmospheric superrotation is a general circulation phenomenon. The entire middle and upper atmosphere rotates in the retrograde direction at speeds reaching approximately 360 kilometers per hour at cloud tops. The winds are significantly weaker near the surface, perhaps 1 to 5 kilometers per hour, but still retrograde. At higher altitudes, the superrotating jet stream dominates. Maintaining this superrotation requires a continuous input of angular momentum to the upper atmosphere, against the dissipative forces that would otherwise slow it down. The mechanism by which this angular momentum is maintained is an active research question. The most widely accepted explanation involves a specific pattern of atmospheric waves, thermal tides driven by solar heating and planetary scale waves driven by the topography of the surface, that transport angular momentum upward from the surface to the upper atmosphere. The relationship between the atmospheric superrotation and the solid planet's retrograde rotation is not entirely clear. The two phenomena, the retrograde spin of the solid planet and the retrograde atmospheric superrotation, are dynamically connected through angular momentum exchange. But which came first and which is driving which is a chicken and egg problem that current models have not definitively resolved. One specific model, sometimes called the wind-induced surface friction model, suggests that the atmospheric superrotation itself exerts a torque on the solid planet through friction at the surface. If the winds near the surface are retrograde, blowing in the same direction as the atmospheric superrotation, they drag the surface in the retrograde direction and accelerate the retrograde rotation of the solid planet. This would mean the atmospheric circulation is contributing to maintaining or accelerating the retrograde spin of Venus's solid body. Whether this effect is large enough to be significant depends on the specific wind speeds near the surface and the efficiency of coupling between the atmosphere and the solid surface. Current atmospheric models of Venus suggest the surface winds are slow, 1 to 5 kilometers per hour, which limits the angular momentum flux. But the coupling, integrated over billions of years, could still be significant. The surface wind coupling is one of the processes that would be characterized by future Venus missions, both through direct wind measurements during descent probes and through high-precision measurements of Venus's rotation rate over time. Let us now talk about the geological evidence relevant to Venus's rotation history, about what the surface of Venus tells us about its past, and whether those clues help distinguish the impact hypothesis from the tidal atmospheric hypothesis. The surface of Venus is dominated by volcanic features, shield volcanoes, volcanic plains, lava flow fields, and more exotic features called coronae and tesserae. The extensive volcanism suggests that Venus has been geologically active for most of its history. But the nature of that activity is quite different from Earth's. Earth has plate tectonics, a system of moving lithospheric plates driven by convection in the mantle. This system recycles the oceanic crust approximately every 100 million years, meaning the oldest preserved oceanic crust is only about 200 million years old. The continental crust is older, but even it has been substantially modified by billions of years of tectonic activity. Venus appears to lack plate tectonics in the Earth sense. Its surface shows no clear evidence of the linear ridges and trenches that characterize Earth's plate boundaries. Instead, Venus appears to have what is sometimes called stagnant lid tectonics, a single rigid lithospheric plate covering the entire planet with no subduction zones. The age of Venus's surface is estimated to be approximately 500 to 700 million years, based on crater counting and geological analysis. This relatively young age suggests that a global resurfacing event occurred approximately 500 million years ago, wiping out all older surface features and producing the relatively fresh volcanic landscape seen today. The nature of this resurfacing event, whether it was a sudden catastrophic overturn of the mantle or a more gradual process, is one of the major open questions in Venus geology. Interestingly, this estimated surface age of 500 to 700 million years coincides with the period within which various dynamical models predict Venus's atmosphere could have reached its current state. If Venus's atmosphere has been substantially restructured multiple times, through giant impacts, through major volcanic episodes, through changes in surface chemistry, the coupling between atmosphere and solid planet that determines the equilibrium rotation state would have evolved over this period. One specific piece of geological evidence with implications for the rotation history is the distribution and character of features called tesserae, high-standing plateaus on Venus with complex, deformed terrains. Tesserae are interpreted as ancient continental crust, material that is older than the surrounding volcanic plains and has survived the resurfacing that reset much of the planet. If tesserae are truly ancient, they may contain the record of Venus's early geological history, including any deformation associated with a giant impact or with rapid changes in rotation rate. The surface geology of Venus is difficult to observe in detail because of the cloud cover. Optical imaging of the surface from orbit is impossible. The Magellan mission's radar mapping provided a global surface map at approximately 100-meter resolution, but lacked the geological context that color imaging and chemical mapping would provide. Future missions, particularly the Veritas orbiter, which will map Venus's surface with higher resolution radar and detect infrared emission from the surface to characterize its composition, will provide the geological context needed to better understand Venus's history. Let us now talk about the axial tilt of Venus, because the orientation of Venus's rotation axis is as strange as its rotation direction and rate, and adds another dimension to the problem. Venus's rotation axis is tilted approximately 177 degrees from the perpendicular to its orbital plane. This means Venus is essentially rotating upside down relative to Earth's orientation. If you define the North Pole as the pole from which the planet appears to rotate counterclockwise, the conventional definition, then Venus's North Pole is pointing approximately toward the south celestial pole rather than the north. This 177-degree tilt is closely related to the retrograde rotation. A planet rotating with its axis tilted 180 degrees would be rotating in the opposite direction from its orbit as seen from above, which is equivalent to retrograde rotation with a normal axial tilt. The 177-degree tilt is 3 degrees short of a full flip, meaning Venus is almost, but not quite exactly, upside down. The 3-degree offset from perfect inversion is significant. If Venus were exactly upside down, 180-degree tilt, it would be rotating directly on the ecliptic plane, and there would be no orbital node precession. The 3-degree offset allows the rotation axis to precess under the influence of solar torques, and the current 177-degree tilt may reflect an equilibrium between the tidal torques trying to align the axis and the precession dynamics. The specific combination of 243-day rotation, retrograde sense, and 177-degree axial tilt is what needs to be explained by any successful hypothesis. The giant impact hypothesis needs to explain how a single collision, or sequence of collisions, could produce this specific combination. The atmospheric tidal hypothesis needs to explain how tidal evolution could produce these specific values from some initial conditions. Some numerical simulations have found that giant impacts can produce the observed combination of retrograde rotation and high axial tilt. But the specific parameter space of impact conditions that leads to the current Venusian state is limited. The impact needs to be in the right mass range, at the right velocity, and at the right angle. This is not physically impossible. Giant impacts of the required scale occurred throughout the early solar system, but it does require a somewhat fortuitous combination of parameters. The atmospheric tidal models have also been explored with numerical simulations. Some of these simulations find that the tidal and atmospheric torques can evolve an initially prograde, rapidly rotating planet to a slowly rotating retrograde state over billions of years. But the specific final state depends sensitively on the initial conditions and on the assumed atmospheric tide strength. Different models with slightly different parameters produce quite different outcomes. Поговорим теперь о том, что конкретно произошло с Венерой, о том, какой именно сценарий наиболее согласуется со всеми имеющимися данными. Wait, let me continue in English. Let us talk about what the best current synthesis of all the evidence suggests happened to Venus, about which combination of mechanisms most naturally explains the retrograde rotation, the slow rotation rate, the axial tilt, and the atmospheric structure. The emerging consensus, if it can be called that given the still active debate, is that Venus's current rotational state is most likely the result of multiple processes operating at different times. In the earliest phase of solar system formation, before the giant impact epoch, Venus likely acquired an initial rotation from the accretion process that was roughly prograde, as expected from the general dynamics of disk accretion. This initial rotation was probably comparable in rate to Earth's initial rotation, perhaps a day of 10 to 30 hours. During the giant impact epoch, the period from approximately 4.5 to 4.0 billion years ago, Venus experienced one or more large impacts that significantly modified its rotation. The specific scenario that best fits the current observations involves a large retrograde impact, an impactor arriving in the retrograde direction that reversed Venus's rotation and established a moderately retrograde spin. This impact may also have significantly increased the axial tilt toward the 177-degree value observed today. After the giant impact epoch, Venus's rotation was governed by the competition between solar tidal torques on the solid planet and solar atmospheric tidal torques on the massive atmosphere. Over the subsequent 4 billion years, this competition evolved Venus toward the current equilibrium state. The specific 243-day rotation period represents the balance point where the two torques are approximately equal and opposite. This picture, impact reversal followed by tidal evolution to a specific equilibrium, is physically consistent with the known physics and has been demonstrated in numerical simulations. It requires an early giant impact of specific but not implausible parameters, and requires the atmospheric tidal torque to be strong enough to prevent complete tidal locking over 4 billion years, which depends on the specific structure of Venus's atmosphere. One key prediction of this model is that Venus's rotation rate should be slowly changing over time as the competition between tidal and atmospheric torques shifts with changing atmospheric conditions. The apparent change in rotation rate measured by Venus Express, the 6.5-minute discrepancy over 16 years, is qualitatively consistent with this prediction, though the cause of the specific measured change is not definitively established. Let us now talk about what Venus's unusual rotation tells us about the diversity of planetary outcomes in the solar system, and what it implies for the habitability of Venus both today and in the distant past. Venus and Earth are often called twins, similar in size, mass, density, and bulk composition. They formed from the same raw materials at similar distances from the Sun. Yet they could not be more different today. Earth has liquid water oceans, a moderate climate, a magnetic field, plate tectonics, and life. Venus has a surface temperature of 465 degrees Celsius, a crushing atmospheric pressure, no water, no magnetic field, no plate tectonics, and, as far as we know, no life. The rotation difference is one of the key factors that contributed to this divergence, but the relationship between rotation and planetary habitability is complex. A faster rotation, which Venus had early in its history if the impact hypothesis is correct, would have driven stronger atmospheric circulation and potentially different climate conditions. A magnetic field, which Venus may have had when its core was still liquid and convecting, would have protected the early Venus from solar wind erosion of its atmosphere. The loss of the magnetic field, possibly connected to the cooling of Venus's core, may have contributed to the loss of water from Venus's early atmosphere. Some models have proposed that early Venus, before whatever catastrophe modified its rotation, may have been habitable. If Venus had liquid water, a magnetic field, and a faster rotation producing more Earth-like atmospheric circulation, the early Venusian climate might have been temperate enough for liquid water to persist at the surface. The period of habitability would have ended when the rotation slowed enough to produce extreme day-night temperature differences, or when the magnetic field was lost and solar wind began stripping the water from the upper atmosphere. This hypothesis, habitable early Venus followed by catastrophic loss of habitability, is speculative but physically plausible. If it is correct, then Venus represents a cautionary tale about how a planet similar to Earth in its initial conditions can evolve to a completely different and hostile state through a combination of rotational and atmospheric evolution. The Da Vinci mission, planned for launch in the late 2020s, will send a probe through Venus's atmosphere, sampling its composition at different altitudes and making measurements designed in part to look for chemical signatures of past water. If early Venus was habitable, if liquid water persisted at the surface for hundreds of millions of years before being lost, the chemical record of that water may be preserved in the noble gas ratios of the current atmosphere. Da Vinci's measurements will constrain models of Venus's atmospheric evolution and provide evidence about whether Venus ever had surface water. Understanding the rotation of Venus is therefore not merely an academic exercise in planetary dynamics. It is connected to the fundamental question of how common habitable worlds are in the galaxy, of how many Earth-like planets in other stellar systems have experienced the kind of rotational and climatic catastrophe that appears to have befallen Venus, and how many have escaped it. If 1 out of 2 terrestrial planets at Earth-like distances from a Sun-like star ends up as Venus, hot, crushing, rotating backward, apparently lifeless, while the other ends up as Earth, temperate, watery, magnetically shielded, teeming with life, then the statistics suggest that habitable Earth-like worlds may be significantly rarer than the total number of terrestrial planets implies. Many of those planets may be Venuses. Or, if early Venus was habitable and became uninhabitable only through a catastrophic process that is relatively rare, the specific giant impact or atmospheric evolution that produced its current state, then the fraction of potentially habitable worlds that actually remain habitable for long periods may be higher than a simple examination of our solar system's current state suggests. The rotation of Venus, backward, slow, strange, is a key piece of evidence in answering these questions. Understanding how it came to be the way it is illuminates the range of outcomes that planetary evolution can produce, and the probability that Earth-like worlds in other systems have followed Earth's path rather than Venus's. Let us talk about the specific measurements and missions that will most directly address the outstanding questions about Venusian rotation in the coming decades. 3 major Venus missions are currently in development or planning. The NASA Veritas mission, Venus Emissivity, Radioscience, INSAR, Topography and Spectroscopy, was selected in 2021 as part of NASA's Discovery program, but subsequently put on hold due to programmatic and budget issues. If it proceeds, it will use radar to map Venus's surface at higher resolution than Magellan, detect infrared emission from the surface to characterize composition, and use radio tracking to measure Venus's gravity field and rotation with unprecedented precision. The NASA Da Vinci mission, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, was also selected in 2021 and is more advanced in development. It will send an instrumented descent sphere through Venus's atmosphere, measuring the composition of the atmosphere from the cloud tops to the surface. The noble gas measurements, argon, neon, krypton, xenon, and their isotopes, will constrain models of Venus's atmospheric origin and evolution, and provide evidence about past water. The ESA Envision mission, selected in 2021 for implementation, will orbit Venus and use a suite of instruments including radar and spectroscopy to characterize the surface, atmosphere, and interior. Envision's radio science experiment will measure Venus's rotation and gravity field with high precision, sufficient to determine whether the rotation rate is changing on decadal timescales, and to constrain the interior structure through measurement of the tidal response. Together, these missions will address the outstanding questions about Venusian rotation from multiple angles. The high-precision rotation measurements from Veritas and Envision will determine the current rotation rate and its time variability. The gravity field measurements will constrain the interior structure and particularly the state of the core. The atmospheric composition measurements from Da Vinci will constrain the history of Venus's atmosphere, including its volatile content and any record of past water. The combination of these measurements with improved numerical models of the tidal and atmospheric dynamics will allow the community to determine which hypothesis, giant impact, tidal evolution, or some combination, best explains Venus's current state, and to reconstruct the sequence of events that led from a newly formed proto-Venus with a prograde rotation to the current, backward, slow-spinning world. Let us talk about what numerical simulations have specifically revealed about the giant impact hypothesis, about the precise parameter space of impacts that can produce Venus's current rotational state, and what these simulations tell us about the likelihood of the impact scenario. The most detailed numerical simulations of giant impacts on Venus mass bodies have been conducted using smoothed particle hydrodynamics, a computational technique that models colliding bodies as large collections of individual fluid particles interacting through gravity and pressure. These simulations can track the fate of material from both the impactor and the target during the collision, and determine the final rotation rate, axial tilt, and angular momentum of the resulting body. The specific results depend sensitively on the impact parameters, the mass of the impactor relative to the target, the impact velocity, and the impact angle. For impacts in the mass ratio range of approximately 0.01 to 0.1, impactors containing 1 to 10% of Venus's mass, arriving at oblique angles of 30 to 60 degrees from the target's surface, the simulations show that retrograde rotation can be produced from initially prograde rotation under some conditions. The challenge is that the post-impact rotation rate is typically much faster than the current Venusian rotation. A successful impact reversal tends to leave Venus rotating with a day of perhaps 20 to 100 hours, still retrograde, but far faster than the current 243 days. Getting from 20 to 100 hours retrograde to 243 days requires additional evolution. This is where the tidal and atmospheric processes become essential even in the impact scenario. Over billions of years after the impact, the solar tidal torque on the solid body, which for retrograde rotation acts to slow the rotation toward zero and then reverse it toward prograde, competes with the atmospheric tidal torque, which, for a massive atmosphere like Venus's, can act to maintain the retrograde rotation. The equilibrium between these two torques determines the final rotation rate. The specific equilibrium rotation period depends on the ratio of the solid body tidal torque to the atmospheric tidal torque. Current models of these torques, calibrated against observations of Venus's atmosphere, predict equilibrium rotation periods in the range of approximately 100 to 300 days for retrograde rotation. The observed 243 days falls within this range, consistent with the scenario where a giant impact established retrograde rotation and subsequent tidal evolution brought the rotation to the current value. This quantitative consistency is one of the strongest arguments for the impact plus tidal evolution scenario. It is not just qualitatively plausible, the specific numbers work out. Let us now talk about the alternative hypothesis in more detail. The scenario in which Venus's current rotation developed entirely through tidal and atmospheric processes without any giant impact reversing an initially prograde rotation. This hypothesis, sometimes called the tidal capture or tidal evolution hypothesis, proposes that Venus began with a prograde rotation that was progressively slowed and eventually reversed by the combined action of solid body tidal torques and atmospheric tidal torques. The scenario requires that the solid body tidal torque be strong enough to slow Venus's rotation to zero, overcoming whatever initial angular momentum Venus had, and then weak enough thereafter that the atmospheric tidal torque can drive the rotation retrograde. The difficulty with this scenario is that reversing a prograde rotation through tidal torques alone, without an impact, requires a specific sequence of events. The solid body tidal torque is always trying to align Venus's rotation with its orbital period. For retrograde rotation, it acts to slow the rotation, stop it, and then accelerate it prograde. For the atmospheric tidal torque to reverse this and maintain retrograde rotation, it must be larger than the solid body tidal torque in the regime where the rotation has slowed nearly to zero. Numerical models of this process have found that for some initial conditions and atmospheric parameters, the system can evolve to a slowly rotating retrograde state without an impact. But the range of initial conditions and parameters that leads to this outcome is narrow. Many combinations of initial rotation rate and atmospheric tide strength lead to prograde tidal locking, or to a different equilibrium state, rather than to the observed retrograde rotation. The tidal evolution scenario without an impact also struggles to explain the 177-degree axial tilt. Tidal torques on a rapidly rotating planet tend to reduce the axial tilt towards zero. They try to align the rotation axis perpendicular to the orbital plane. Getting Venus's tilt to 177 degrees through tidal evolution alone, without an impact, requires specific combinations of orbital mechanics and tidal parameters that are not generic. This does not rule out the tidal evolution hypothesis. It simply means that if Venus reached its current state through purely tidal evolution, the initial conditions must have been quite specific. An impact hypothesis requires a specific impact event. A tidal hypothesis requires specific initial conditions. Neither is obviously more likely a priori, but the giant impact epoch provides a natural mechanism for producing a wide range of initial conditions through the stochastic process of large body collisions. Let us now talk about what other solar system bodies tell us about retrograde rotation, about whether Venus is truly unique, or whether other examples of unusual rotation in the solar system illuminate the possible mechanisms. Uranus, the ice giant, has an axial tilt of approximately 98 degrees, making it rotate nearly on its side. Its rotation is technically prograde, but just barely. The tilt is so large that one pole points almost directly toward the Sun during Uranus's summer. The standard explanation for Uranus's extreme tilt is a giant impact, a large body striking Uranus early in its history and knocking it sideways. The impact would need to have been massive, perhaps as large as a few percent of Uranus's mass, to produce the 98-degree tilt. The parallel with Venus is instructive. Both Venus and Uranus have rotational anomalies that are most naturally explained by giant impacts. Impacts that delivered angular momentum in unusual directions, or that reversed the direction of existing angular momentum. Both anomalies are broadly consistent with the types of large impacts that were common during the early solar system's chaotic assembly phase. Pluto, the dwarf planet, is in a mutual tidal lock with its large moon Charon. Both Pluto and Charon rotate with the same period as their mutual orbital period. They always keep the same faces toward each other. This extreme tidal evolution, from whatever initial rapid rotation Pluto had to the current tidally locked state, shows that tidal forces can dramatically alter rotation over billions of years, even for relatively small bodies at large distances from the Sun. If tides can fully tidally lock Pluto-Charon, the possibility that tides have significantly altered Venus's rotation over 4.5 billion years is physically well supported. The Moon itself is tidally locked to Earth, rotating once per orbit, always keeping the same face toward Earth. The Moon's tidal locking happened much faster than Venus's rotational evolution, within a few 100 million years of formation, because the Earth-Moon tidal forces are much stronger than the Venus-Sun tidal forces. But the physics is the same. Tidal forces can dramatically alter rotation. Mercury is not tidally locked in the simple sense. It does not rotate once per orbit. Instead, it is in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits. This resonance is thought to be a consequence of Mercury's orbital eccentricity. The non-circular orbit creates asymmetries in the tidal force that favour the 3-to-2 resonance over simple tidal locking. Mercury's current state is therefore the result of billions of years of tidal evolution, with the specific outcome determined by the orbital eccentricity. These examples, Uranus's tilted rotation from an impact, Pluto's mutual tidal lock, Mercury's 3:2 resonance, collectively illustrate that extreme rotational states in the solar system are not unusual. Giant impacts can produce dramatic tilts and reversals. Tidal evolution can produce locking and resonances. The specific rotational state of any given body is the outcome of its entire history, the initial conditions set by formation and early impacts, modified by billions of years of tidal and atmospheric evolution. Venus's retrograde rotation is unusual, but it is unusual in the way that a specific historical accident is unusual. It is the outcome of a specific sequence of events that Venus experienced and Earth did not. It is not a violation of physical principles, but a product of them. Let us now talk about what Venus's rotation means for its climate, for the specific way the planet's extreme rotational state has shaped its atmosphere and surface temperature. The 243-day retrograde rotation has profound implications for Venusian climate. On Earth, the 24-hour rotation rate drives vigorous atmospheric circulation. The Coriolis effect from Earth's rapid rotation deflects winds and produces the complex pattern of trade winds, jet streams, and weather systems. On Venus, the extremely slow rotation means the Coriolis effect is almost negligible for large-scale atmospheric circulation. The dominant driver of Venusian atmospheric circulation is not rotation, but the day-night temperature difference. With a day lasting 116 Earth days, the sunlit hemisphere is heated for an extended period, while the night side is in darkness. This extreme differential heating, combined with the massive carbon dioxide atmosphere, drives a global circulation pattern very different from Earth's. The remarkable thing is that despite the slow rotation and extreme differential heating, Venus's surface temperature is nearly uniform, approximately 465 degrees Celsius everywhere, at all latitudes, on both the day side and night side. This uniformity results from the thick, dense atmosphere being extraordinarily efficient at distributing heat globally. The massive atmosphere acts as a thermal buffer, absorbing heat on the day side, transporting it to the night side, and maintaining a nearly constant temperature everywhere. The atmospheric superrotation, the rapid circulation of the upper atmosphere in the retrograde direction, is the primary mechanism of this global heat transport. Winds at cloud-top altitudes of 65 kilometers reach approximately 360 kilometers per hour and complete a circuit of the planet in approximately 4 days. This rapid circulation carries heat from the day side to the night side far more efficiently than the solid planet rotates. The specific character of Venusian atmospheric circulation, dominated by the retrograde superrotation and largely independent of the surface rotation, means that the planet's climate is somewhat insulated from the extreme slowness of its rotation. Even if Venus rotated somewhat faster or slower, the dense carbon dioxide atmosphere would still efficiently distribute heat and maintain relatively uniform surface temperatures. But this does not mean the rotation rate is entirely irrelevant to Venusian climate. The specific strength and character of the atmospheric superrotation, which drives the global heat transport, itself depends on the rotation rate through complex dynamics. The maintenance of the superrotation involves waves, thermal tides, and planetary scale waves, whose character depends on the ratio of the planetary rotation rate to the atmospheric circulation rate. Change the rotation rate, and the superrotation might be maintained at a different speed, or might not be maintained at all. If early Venus rotated faster, as the giant impact hypothesis implies, the early Venusian atmosphere would have been different. A faster rotation would have driven stronger Coriolis effects and a more Earth-like atmospheric circulation, more banded wind patterns, more organized weather systems. The specific thermal properties of the early Venusian atmosphere are important for determining whether early Venus could have been habitable, whether the faster rotation drove sufficient atmospheric circulation to maintain more moderate temperatures before the greenhouse effect had fully developed. These questions connect the rotation history of Venus directly to questions about its past habitability, questions that the Da Vinci, Veritas, and Envision missions are designed to address through chemical and geological measurements. Let us now talk about the surface of Venus in more detail and what the geological record tells us about the sequence of events in Venus's history that may have been connected to or caused by its rotational evolution. The surface of Venus, as mapped by Magellan, shows a geologically diverse world, but one with a specific character very different from Earth. Approximately 80% of the surface is covered by lowland volcanic plains, relatively flat areas covered by extensive lava flows from ancient volcanic eruptions. The remaining 20% includes highland plateaus, most notably Ishtar Terra in the north and Aphrodite Terra along the equator, and various other geological features. The most distinctive geological features of Venus are the coronae, roughly circular features ranging from approximately 100 to 1,000 kilometers in diameter, that are interpreted as the surface expression of upwelling mantle plumes. Coronae form when a hot plume of mantle material rises beneath the crust, domes the surface upward, and then subsides as the plume dissipates, leaving a roughly circular depression surrounded by an annular ring of ridges and fractures. Venus has approximately 500 identified coronae distributed across its surface. The extensive coronae and volcanic plains suggest that Venus's geological history has been dominated by mantle plume volcanism rather than plate tectonics. Without the subduction zones and spreading centers of plate tectonics, Venus does not have a mechanism to continuously recycle its crust. Instead, volcanic activity occurs at specific hotspots, driven by mantle plumes rising through the stagnant lithosphere, and the surface gradually accumulates volcanic material until some overturn event resets the system. The global resurfacing event approximately 500 to 700 million years ago, inferred from the relatively young age of the surface and the uniform crater distribution, may represent exactly such an overturn. The mantle may have accumulated enough heat over billions of years, trapped by the stagnant lid, that it eventually became unstable and overturned, producing a brief but intense episode of global volcanism that resurfaced essentially the entire planet. This catastrophic resurfacing would have had dramatic consequences for the atmosphere, releasing enormous amounts of volcanic gases, including water vapor, carbon dioxide, and sulfur dioxide. These volcanic emissions would have significantly altered the composition and mass of the atmosphere, potentially strengthening the greenhouse effect and pushing Venus toward its current extreme climate. The timing of the global resurfacing, approximately 500 million years ago, is recent enough that it may have significantly altered Venus's atmospheric structure after the rotation had already reached its current quasi-equilibrium state. Or the resurfacing may have perturbed the atmospheric structure enough to shift the equilibrium rotation slightly. The apparent change in rotation rate measured by Venus Express might reflect ongoing adjustment of the atmosphere to relatively recent volcanic events. The relationship between Venus's geological history, its volcanic resurfacing events, its lack of plate tectonics, its unusual interior structure, and its rotational evolution is a complex one that future missions will help unravel. The surface geology provides a record of Venus's past activity, while the rotation provides a dynamic constraint on the atmospheric and tidal evolution. Combining these two lines of evidence with improved interior structure measurements will allow the reconstruction of Venus's complete evolutionary history in more detail than is currently possible. Let us now talk about the specific comparison between Venus and Earth that the rotation problem illuminates, about what the different outcomes of these two apparently similar planets tells us about the role of contingency and catastrophe in planetary evolution. Venus and Earth formed from essentially the same raw materials, the same mixture of rocky and metallic materials at similar distances from the Sun. They have similar masses, similar bulk densities, similar initial abundances of the major rock-forming elements. By all naive expectations, they should have evolved similarly, two Earth-like planets in the same solar system. The divergence between them is real and dramatic. Earth has a rapidly rotating, magnetically shielded, water-covered, plate tectonically active, life-bearing surface. Venus has a slowly rotating, magnetically unshielded, water-free, stagnant lid, apparently lifeless hellscape. The rotation difference is one of the key factors in this divergence. Earth's rapid rotation, approximately 24 hours, drives the Coriolis effect that organizes atmospheric and oceanic circulation. The organized circulation distributes heat more efficiently and helps maintain moderate polar temperatures. Earth's rapid rotation also maintains the geodynamo, the convection in the liquid outer core that generates the magnetic field through the Coriolis effect on the convecting fluid. The magnetic field protects Earth's atmosphere from solar wind stripping and may have been important for maintaining the water inventory over billions of years. Venus's slow retrograde rotation, whatever its cause, has contributed to both the absence of a magnetic field and the different atmospheric circulation pattern. Without a magnetic field, Venus's upper atmosphere is more exposed to solar wind stripping. The slow rotation produces weaker Coriolis effects and a different circulation pattern that may be less efficient at distributing heat at certain altitudes. The question of whether the rotation difference between Venus and Earth is the cause of their divergent evolutionary paths, or the consequence of those paths, or both, is not fully resolved. The divergence may have begun with a single catastrophic event, the giant impact that reversed Venus's rotation, and then been amplified by feedback processes as the slow rotation, the loss of the magnetic field, and the greenhouse effect reinforced each other over billions of years. Or the divergence may have had multiple causes acting simultaneously and independently, the rotation reversal being one factor among several, including different initial volatile inventories, different interior cooling histories, and different amounts of late volatile delivery from impactors. Disentangling these possibilities requires understanding Venus's history in detail, and that detail can only be obtained through the kinds of measurements that the upcoming generation of Venus missions will provide. The rotation measurements from Envision and Veritas will constrain the current dynamical state. The atmospheric composition measurements from Da Vinci will constrain the volatile history. The geological mapping will constrain the tectonic and volcanic history. Together, these measurements will allow the reconstruction of the sequence of events that led from a similar starting point to two radically different worlds. And that reconstruction will illuminate not just the history of Venus, but the range of outcomes that planetary evolution can produce throughout the galaxy. Let us now talk about one more aspect of the Venusian rotation problem that deserves attention: the role of the near resonance between Venus's rotation and its orbit in maintaining the current state. Venus's sidereal rotation period, 243.0185 Earth days, and its orbital period, 224.701 Earth days, are in an almost exact ratio. The ratio of the orbital period to the rotation period is approximately 0.9245, close to, but not exactly, a simple rational number. The synodic rotation period, the time it takes Venus to rotate once relative to the Sun as seen from Venus, is approximately 116.75 Earth days, which is close to half the Venus-Earth synodic period of approximately 583.9 Earth days. This near resonance between Venusian rotation and the Venus-Earth synodic period was noted decades ago and led to speculation that Venus might be in an exact resonance with Earth, always presenting the same face to Earth at closest approach. This would be analogous to the Moon's synchronous rotation with Earth, but involving an orbital resonance rather than a tidal lock. However, more precise measurements have shown that Venus does not present exactly the same face to Earth at closest approach. The resonance is approximate rather than exact. The near coincidence may simply be a coincidence. The current rotation rate happens to be close to the value that would produce a resonance with Earth's orbit without actually being locked into it. Whether this near resonance is physically meaningful, whether Earth's gravity plays any role in maintaining Venus's current rotation period, has been studied but not definitively resolved. Earth's gravitational influence on Venus is much weaker than the Sun's influence, and quantitative models suggest that Earth's tidal effect on Venus is too small to maintain a resonance. The near coincidence is most likely just a coincidence. But the coincidence is not exact, and the small deviation from exact resonance is one of the quantities that will be measured with high precision by future missions. If the deviation from resonance is decreasing with time, if Venus's rotation period is slowly approaching the exact resonance value, that would suggest Earth's gravity is playing a role. If the deviation is not systematically changing, the resonance is most likely coincidental. The rotation of Venus, backward, slow, tilted, resonant-ish, is a problem that has occupied planetary scientists for 6 decades. The basic facts have been known since the 1960s. The physical mechanisms that could explain them have been discussed for just as long. But the definitive answer, the specific sequence of events that produced Venus's current rotational state, remains elusive. This is not for lack of ideas. The physics is well understood. The numerical tools are sophisticated. The hypotheses, giant impact, tidal evolution, atmospheric tides, are physically well motivated and have been explored quantitatively. The problem is that the evidence needed to discriminate definitively between the hypotheses has not yet been obtained. That evidence is coming. The upcoming missions will measure Venus's rotation with unprecedented precision. They will characterize its interior structure. They will analyze its atmospheric composition for chemical signatures of past water and past volcanic activity. They will map its surface in detail that the Magellan mission could not achieve. And from all of these measurements, a clearer picture of Venus's history will emerge. Perhaps the impact hypothesis will be confirmed. Specific geological signatures of a giant impact will be found in the surface record. Or the interior structure will be shown to be consistent with a massive early collision. Perhaps the tidal evolution hypothesis will prevail. The atmospheric measurements will show that the current atmospheric state is exactly what is needed to maintain the retrograde rotation through tidal torque balance. Perhaps neither hypothesis will be definitively confirmed, and a more complex scenario, a sequence of events unique to Venus's specific history, will be required. Whatever the answer turns out to be, it will illuminate not just the history of one nearby planet, but the fundamental question of how similar starting conditions can produce radically different outcomes, and what that diversity implies for the prevalence of habitable worlds throughout the galaxy. Venus spins backward for a reason. Something terrible happened long ago, or a long sequence of subtle processes conspired to produce the current state. Either way, Venus carries the record of what happened in its rotation, its atmosphere, its geology, and its interior. We are finally developing the tools to read that record. The answer is written in the backward spin of a nearby world. We just need to learn how to read it properly. Let us talk about what the specific chemistry of Venus's atmosphere reveals about its history, and why the particular composition of the Venusian atmosphere is itself a clue to whatever catastrophe or process produced the current rotational state. Venus's atmosphere is dominated by carbon dioxide, approximately 96.5%, with nitrogen making up most of the remainder. The surface pressure of 92 atmospheres means the total mass of carbon dioxide in Venus's atmosphere is approximately 100 times greater than the total mass of all gas in Earth's atmosphere. If Earth's carbonate rocks, the limestone and dolomite that have stored carbon dioxide over billions of years through weathering and biological processes, were outgassed into the atmosphere, Earth would have an atmosphere very similar to Venus's. The difference between Earth and Venus in terms of atmospheric carbon dioxide is not a difference in the total amount of carbon, it is a difference in where that carbon is stored. On Earth, the carbon dioxide silicate weathering cycle, the process by which atmospheric CO2 dissolves in rainwater to form carbonic acid, which then weathers silicate rocks and deposits carbonate minerals, acts as a thermostat for the climate over geological timescales. When temperatures rise, weathering accelerates, removing CO2 from the atmosphere and cooling the planet. When temperatures fall, weathering slows, allowing volcanic outgassing to build CO2 back up and warming the planet. This feedback has maintained Earth's surface temperature in the liquid water range for approximately 3.8 billion years, despite the Sun brightening by approximately 30% over that period. Venus appears to lack this thermostat. Either Venus never had the liquid water needed to drive silicate weathering, or it had liquid water early in its history and lost it before the feedback mechanism could operate effectively. If early Venus had liquid water and a functioning weathering cycle, the carbon would have been sequestered in carbonate rocks, as on Earth. At some point, the liquid water was lost and weathering stopped. The carbonate rocks were then exposed to the high surface temperatures and decomposed, releasing their stored carbon dioxide into the atmosphere and accelerating the greenhouse effect in a runaway feedback. The noble gas composition of Venus's atmosphere provides specific chemical constraints on this history. Noble gases, helium, neon, argon, krypton, and xenon, are chemically inert and do not participate in atmospheric chemistry or weathering. Their abundances and isotopic ratios in the atmosphere therefore preserve a record of the sources and losses of gas from Venus's atmosphere over its history. The argon-36 and argon-38 abundances primordial argon delivered to Venus during its formation, can be compared to Earth's values to constrain how Venus's initial volatile inventory compares to Earth's. The argon-40 abundance, radiogenic argon produced by the decay of potassium-40 in the interior, constrains the total amount of volcanic outgassing that has occurred over Venus's history. The xenon isotopic composition, which is sensitive to atmospheric escape processes, constrains the history of atmospheric loss to space. These measurements are at the core of the Da Vinci science objectives. The descent probe will measure the noble gas composition of Venus's atmosphere with much higher precision than any previous mission, providing definitive constraints on whether Venus formed with a different initial volatile inventory than Earth, whether early Venus had liquid water, and how much atmospheric loss has occurred over its history. If Venus formed with similar initial water content to Earth, which is expected given their similar formation environment, and if that water was subsequently lost, the noble gas record should show the signature of this loss. Different atmospheric escape processes, thermal escape, non-thermal escape driven by solar wind, impact erosion, leave different isotopic signatures in the noble gases. The Da Vinci measurements will distinguish between these escape mechanisms and constrain when the water was lost. The timing of water loss from Venus is crucial for understanding the connection between the rotational history and the atmospheric evolution. If Venus lost its water within the first billion years, before the slow retrograde rotation was fully established, the water loss may not be directly connected to the rotation. If the water loss occurred more recently, associated with the global resurfacing event 500 to 700 million years ago, it may have been triggered by volcanic outgassing that overwhelmed the weathering capacity of whatever liquid water remained. Either scenario has implications for the habitable period of early Venus, a period that may have lasted hundreds of millions of years, and during which the faster rotation might have maintained more Earth-like conditions. Let us now talk about what the global resurfacing event on Venus specifically, the volcanic catastrophe approximately 500 to 700 million years ago, can tell us about the connection between interior dynamics, surface geology, and rotational evolution. The evidence for a global resurfacing event on Venus comes primarily from the statistical distribution of impact craters on the surface. Venus has approximately 1,000 identified impact craters, a relatively small number for a planet of its size. More significantly, the craters are distributed nearly uniformly across the surface. There are no regions with dramatically more craters than others, which would indicate older terrain. This uniformity suggests that essentially the entire surface was reset to zero crater count at approximately the same time, approximately 500 to 700 million years ago, through a global resurfacing event that buried all older craters. The nature of this resurfacing event is debated. The two main hypotheses are catastrophic overturn and equilibrium resurfacing. The catastrophic overturn hypothesis proposes that Venus's mantle periodically reaches a state where the cold, dense lid of lithosphere becomes gravitationally unstable and founders, sinking into the mantle, while hot mantle material wells up to replace it. This overturn would produce an intense but brief episode of global volcanism that rapidly resurfaces the entire planet. The model predicts that Venus alternates between periods of quiescence, with a stable, stagnant lid, and periodic catastrophic overturns every few hundred million to billion years. The equilibrium resurfacing hypothesis proposes that Venus's volcanism is less episodic, that resurfacing occurs continuously, but at a rate that has periodically been high enough to obliterate craters across the surface. In this model, the uniform crater distribution reflects a resurfacing rate that has been relatively constant rather than a single catastrophic event. The distinction between these models has implications for Venus's current geological state. If catastrophic overturns are the relevant mechanism, Venus may currently be in a quiescent period. Accumulated heat in the mantle is slowly building toward the next overturn. The current volcanic activity, which appears to be occurring at some locations, as discussed below, would be localized hotspot activity rather than global resurfacing. Recent evidence suggests that Venus is currently volcanically active. Analysis of infrared data from the Venus Express spacecraft, specifically the VIRTIS instrument, which measured thermal emission from the surface at near-infrared wavelengths, found temporal variations in the infrared brightness of certain volcanic regions consistent with fresh lava flows. The Atla Regio region, a large volcanic dome in the equatorial highlands, showed brightness variations over a period of months that are most naturally explained by active lava eruption. This evidence for current volcanic activity on Venus, while not conclusive, suggests that Venus's interior is not fully quiescent and that the process of volcanic outgassing into the atmosphere is ongoing. Continued volcanic outgassing maintains the current atmospheric composition and may be contributing to the exchange of angular momentum between the interior and the atmosphere. The connection between current volcanism and the rotational evolution is through the atmospheric angular momentum budget. When volcanoes erupt, they release gases into the atmosphere, altering the atmospheric mass distribution and potentially affecting the atmospheric circulation. Changes in atmospheric circulation affect the atmospheric tidal torque, which in turn affects the solid planet's rotation rate. The apparent change in Venus's rotation rate, measured by Venus Express over 16 years, if real, may in part reflect changes in atmospheric angular momentum driven by volcanic activity. This connection between volcanism, atmospheric dynamics, and rotation illustrates the deeply coupled nature of Venus's evolution. The rotation affects the atmosphere affects the climate affects the weathering affects the carbon cycle affects the volcanic activity, and the volcanic activity affects the atmosphere and the rotation. Understanding any one of these connections requires understanding all of them. Let us now talk about what exoplanets, planets orbiting other stars, tell us about the relevance of the Venus rotation problem to planetary science more broadly. The discovery of exoplanets over the past 3 decades has transformed our understanding of planetary systems. We now know that planets are extraordinarily common. Essentially, every Sun-like star appears to have planets of some kind. The distribution of exoplanet sizes and orbital periods has revealed a surprising diversity, from hot Jupiters orbiting in a few days to super-Earths and mini-Neptunes that have no solar system analogue, to Earth-sized planets in habitable zone orbits around M-dwarf stars. Among the most interesting category for the Venus comparison are exovenuses, rocky planets at Venus-like distances from their host stars that may have Venus-like atmospheric and rotational properties. Detecting and characterizing exovenuses is difficult. They are too close to their host stars for direct imaging, and transit spectroscopy can characterize their atmospheres but not their surface conditions or rotation. Nevertheless, theoretical arguments and statistical inference suggest that a significant fraction of rocky planets in the inner habitable zone, planets similar to Venus in size and orbital distance, may have undergone Venus-like evolution. The fraction of rocky planets that become Venus-like versus Earth-like has important implications for the prevalence of life in the galaxy. If most rocky planets in Venus-like orbits end up as Venus, hot, crushing, apparently lifeless, and if only a minority end up as Earth, moderate, watery, life-bearing, then the number of potentially habitable worlds is substantially reduced from naive estimates based on the total number of rocky planets. Understanding the Venus rotation problem is therefore directly relevant to estimating the prevalence of life in the galaxy. If Venus's retrograde rotation was caused by a specific giant impact, a relatively rare stochastic event, then Venus-like evolution may be relatively rare, and most Venus-orbit rocky planets may have followed a different path. If Venus's retrograde rotation evolved through more deterministic tidal processes that would operate on any similar planet, then Venus-like evolution may be the norm for inner habitable zone rocky planets, and Earth-like evolution the exception. The TRAPPIST-1 system, 7 Earth-size planets orbiting a small M-dwarf star approximately 40 light-years from Earth, is the most intensively studied multi-planet system for habitability. 3 of the 7 planets, TRAPPIST-1, E, F and G, orbit in the habitable zone of their star. But because their star is a red dwarf, they are likely tidally locked, rotating once per orbit, always keeping the same face toward the star. Their rotation is therefore neither Earth-like nor Venus-like. It is in a different regime entirely. For rocky planets orbiting Sun-like stars, where tidal locking at Venus-like distances would not occur in the age of the universe, the question of whether the planet ends up with Earth-like prograde rotation or Venus-like retrograde rotation becomes relevant. The answer likely depends on the specific history of giant impacts during the planet's formation, and this history is stochastic, different for each planet in each system. The Venus rotation problem is therefore a specific instance of a broader question about planetary diversity. How much of the difference between planets like Venus and Earth reflects deterministic processes acting on similar initial conditions versus stochastic events like specific giant impacts that could have gone differently? The answer to this question determines the variance in planetary outcomes for a given set of initial conditions, and therefore the range of environments that life might potentially inhabit throughout the galaxy. Let us now talk about the specific predictions that the competing hypotheses make for future observations, about what InVision, Veritas and Da Vinci will specifically find if the giant impact hypothesis is correct versus if the tidal evolution hypothesis is correct. If the giant impact hypothesis is correct, several specific observational signatures might be preserved in Venus's current state. First, the interior structure should show signs of a major early impact. Giant impacts heat and mix the interior, potentially melting a large fraction of the planet and producing a magma ocean that then differentiates. The differentiation products, the specific distribution of iron and silicate and radioactive elements within the planet, would be different from a planet that formed more gradually. EnVision's measurement of Venus's tidal deformation, the degree to which the planet distorts in response to the Sun's tidal force, is sensitive to the interior viscosity and rigidity, which in turn reflects the thermal history and differentiation state. Second, the ancient terrains, the tesserae that represent the oldest preserved surface, might contain geological signatures of the impact. Very large impacts can produce globally distributed ejecta, pressure metamorphism of surface rocks, and other geological evidence. The surface mapping from Veritas at higher resolution than Magellan might reveal features in the tesserae consistent with ancient impact processing. Third, the noble gas composition measured by Da Vinci might show signatures consistent with early atmospheric loss associated with a giant impact. Very large impacts can strip a planet's atmosphere. The impact energy vaporizes and accelerates atmospheric gas to escape velocity. The isotopic fractionation produced by such impact-driven atmospheric loss leaves specific signatures in the noble gas ratios. If Venus experienced a large retrograde impact early in its history, the noble gas record might preserve the signature of the associated atmospheric stripping. If the pure tidal evolution hypothesis is correct, no giant impact, just billions of years of tidal and atmospheric evolution, the expected signatures would be different. The interior structure would reflect a more typical differentiation history, no signature of an anomalously large early impact. The tesserae would not show unusual impact processing. They would simply be ancient continental crust with a typical geological history. The noble gas ratios would reflect steady atmospheric evolution without the sudden loss event associated with an impact. The rotation measurements themselves will distinguish between the hypotheses in a more indirect way, by constraining whether the current rotation rate is exactly at the atmospheric tidal equilibrium value or whether it is still evolving toward equilibrium. If Venus's rotation is at a stable equilibrium, maintained by the balance between solid body tidal torque and atmospheric tidal torque, the rotation rate should be essentially constant on decadal timescales, except for small fluctuations due to atmospheric variability. If Venus's rotation is still evolving toward equilibrium from a post-impact state, still slowing down or speeding up toward the equilibrium value, a systematic trend in the rotation rate should be detectable. The Venus Express measurement of a 6.5-minute discrepancy over 16 years, if real and systematic, would be consistent with ongoing evolution toward equilibrium rather than a stable equilibrium state. The higher precision measurements from Envision and Veritas will determine whether this trend is real and characterize its magnitude. Let us now talk about the broader lesson that Venus teaches us about the concept of planetary habitability, about how a world can transition from potentially habitable to definitively uninhabitable, and what factors determine whether such a transition occurs. Habitability, the capacity of a planetary environment to support life as we know it, requires several conditions to be met simultaneously over geological timescales. Liquid water must be present at the surface or subsurface. Temperatures must be within the range where water remains liquid and complex chemistry can operate. The chemical building blocks of life must be available, and the environment must be stable enough over sufficient timescales for life to originate and evolve. Earth has maintained these conditions for approximately 3.8 billion years, from the earliest evidence of life to the present. This persistence over such a long timescale is itself remarkable. The Sun has brightened by approximately 30% over this period, the Moon has receded, and Earth's rotation has slowed. Continents have drifted, and climates have changed dramatically. Yet liquid water has been maintained, and life has persisted. Venus may have maintained habitable conditions for a much shorter period, perhaps a few 100 million to 1 billion years early in its history. If so, life on Venus, if it ever arose, would have had a much shorter window in which to develop. Whether a billion years is long enough for life to originate and evolve to a level of complexity that might be detected in the geological or atmospheric record is an open question. Life on Earth originated within roughly the first billion years of the planet's existence, suggesting that the origin of life may not require the full several billion years available. The transition from habitable to uninhabitable Venus appears to have been driven by a combination of factors. The loss of liquid water, possibly connected to early volcanic activity, the runaway greenhouse effect, and possibly the loss of the magnetic field that once protected the upper atmosphere from solar wind stripping. The rotation history, whether a giant impact reversed the rotation early on or tidal evolution produced the current state more gradually, affects the timing and character of these transitions. If the giant impact that reversed Venus's rotation occurred very early, within the first 100 million years, the subsequent rotational and atmospheric evolution proceeded from a retrograde state for essentially all of Venus's history. The early Venus would have had a retrograde but potentially faster rotation than today, perhaps a day of 50 to 100 hours retrograde, which might still have been compatible with moderate climates if the atmosphere was less massive than today. If the rotation reversal occurred later, after the planet had already developed a substantial atmosphere and perhaps liquid water, the impact itself would have had dramatic consequences for the existing environment. A large impact sufficient to reverse Venus's rotation would deliver enormous energy to the surface and atmosphere, melting the crust, vaporizing oceans if they existed, and catastrophically disrupting whatever climate had previously existed. This scenario, late impact reversing a previously habitable world, would represent one of the most dramatic examples of catastrophic habitability loss in solar system history. Distinguishing between early and late impact scenarios is another goal of future Venus missions. The timing of the impact should, in principle, be constrainable from the geological record. If the impact occurred when Venus had a mature crust, the record of the impact should be more easily preserved than if it occurred during the magma ocean phase, when the entire surface was being continuously reshaped by volcanic activity. This is the specific challenge of Venus science, separating the record of events that occurred 4.5 billion years ago from the overprinting of 4 billion years of subsequent volcanic and atmospheric activity. The ancient tesserae represent the best opportunity to access this early record, but even they have been modified by billions of years of surface processing. Let us now talk about one more dimension of the Venus rotation problem, the question of whether the current rotation state is truly stable or whether it might change significantly in the future. The current rotation of Venus, 243 days retrograde, represents an approximate equilibrium between solid body tidal torques and atmospheric tidal torques. But this equilibrium is approximate. The two torques are not perfectly balanced, and the rotation rate is slowly evolving. The question is whether it is evolving toward a more stable equilibrium or away from one. If the rotation rate is currently at a stable fixed point, a true equilibrium where small perturbations are damped back to the equilibrium value, Venus will remain in its current rotational state indefinitely, as long as the atmospheric structure remains approximately constant. Small changes in volcanic outgassing or atmospheric chemistry would produce small perturbations to the equilibrium, but the system would return to approximately the same state. If the rotation rate is at an unstable fixed point, an equilibrium where small perturbations grow rather than damp, Venus might eventually transition to a very different rotational state. Possible outcomes include eventual prograde tidal locking, where the solid body tidal torque wins and the planet slowly tilts towards synchronous rotation, or a transition to a different retrograde equilibrium with a different rotation period if the atmospheric structure changes sufficiently. The long-term evolution of Venus's rotation is also affected by the evolution of the Sun. As the Sun slowly brightens over the next billion to 5 billion years, the solar tidal forces on Venus will increase, because tidal forces depend on the solar luminosity through the atmospheric tide component. As solar heating increases, the atmospheric tidal torque may strengthen relative to the solid body tidal torque, potentially shifting the equilibrium toward a different rotation rate. Whether this shift is slow and monotonic or involves transitions between different equilibrium states is not well understood. The ultimate fate of Venus's rotation, like the fate of Earth's rotation, will be determined by the evolution of the Sun into a red giant approximately 5 billion years from now. As the Sun expands, its tidal forces on Venus will increase enormously. The red giant Sun will produce tidal forces billions of times stronger than the current values, strong enough to completely dominate the atmospheric tidal torque and drive Venus toward tidal locking on relatively short timescales. The 243-day retrograde rotation that Venus currently maintains will be overwhelmed by the tidal forces of the dying Sun, and Venus will be tidally locked, or possibly engulfed, before the Sun's red giant phase is complete. This gives Venus's current rotation a finite lifetime, not in any human relevant sense, but in the cosmic sense. The backward spin that has defined Venus for possibly billions of years will eventually be overwritten by the tidal forces of an expanding Sun. Before that happens, long before, Venus's surface will have been sterilized by the increasing solar luminosity. Whatever secrets are currently preserved in the rocks of the ancient tesserae will have been erased. This impermanence of planetary geological records, the eventual erasure of even the most ancient geological evidence by the processes that accompany stellar evolution, is one reason why understanding Venus now, with the missions we are currently planning, is scientifically urgent. The record of what happened in the early solar system, the giant impacts, the volatile delivery, the magnetic field evolution, the atmospheric history, is preserved in Venus's surface and interior in forms that are not permanent. The upcoming missions represent a window of opportunity to read this record before it is further obscured. Venus spins backward. It has been spinning backward for billions of years, perhaps since an enormous collision reversed its rotation in the chaotic early solar system, perhaps through a more gradual tidal and atmospheric evolution that produced the same result through different means. The specific mechanism remains uncertain. The evidence needed to resolve the uncertainty is coming. What is certain is that the backward spin is not arbitrary. It is the outcome of a specific history, a history written in the rotation rate, in the atmospheric composition, in the surface geology, and in the interior structure of a world that formed in the same cloud of gas and dust as Earth, but followed a profoundly different path. Understanding that path, understanding why Venus went where it went while Earth went somewhere else, is one of the most important open problems in planetary science. Because Venus's path is not unique to Venus. Somewhere in the galaxy, around the hundreds of billions of stars that exist, orbiting in the habitable zones where liquid water is possible, there are planets that formed under conditions similar to Earth's and followed paths similar to Venus's. Understanding Venus helps us understand them. Understanding how one world goes wrong while another goes right helps us understand how common worlds that go right, worlds that maintain liquid water and moderate temperatures and the conditions for life, really are. The answer to why Venus spins backward may be the answer to a much larger question. How many Earths are there in the galaxy, and how many Venuses? On a clear night, when Venus is visible, and it is often the brightest object in the sky after the Moon, unmistakable, blazing white in the west after sunset or the east before sunrise, you can look at it and know something specific. That light is real. It is sunlight reflected from a world 261 million kilometers away at its closest. The photons reaching your eye left the Venusian cloud tops approximately 14 minutes ago. They traveled across empty space at 299,792 kilometers per second and arrived at your retina carrying information about the reflectivity of a sulfuric acid cloud deck 65 kilometers above a surface hot enough to melt lead. And beneath those clouds, rotating right now, tonight, while you look at it, is a world spinning in the wrong direction. Not wobbling, not tilted in an unusual way, actually rotating the other way. If you could watch Venus from directly above its north pole, you would see it turning clockwise. Every other planet turns counterclockwise. The Sun turns counterclockwise. The entire solar system inherited its rotation from the gas cloud that collapsed to form it 4.6 billion years ago, and that rotation was counterclockwise. Venus kept the wrong angular momentum. Something happened to Venus. Something changed it, fundamentally, permanently, billions of years ago. The most likely answer involves an enormous collision. In the first few 100 million years of the solar system's history, the inner planets were being assembled from smaller bodies, planetary embryos crashing together at velocities of kilometers per second, building the final planets through a sequence of impacts that grew progressively larger and more violent. One of these impacts, a body perhaps the size of a small planet, perhaps containing a few percent of Venus's total mass, struck the proto-Venus from the retrograde direction. The collision lasted minutes. The energy released was incomprehensible, heating the crust to thousands of degrees, vaporizing rock and metal into a cloud of debris, delivering enough angular momentum in the opposite direction that the planet's rotation slowed, stopped, and reversed. After that, billions of years of tidal evolution. The Sun's gravity pulling on Venus's massive atmosphere one way and on the solid planet another way. Two competing torques reaching an equilibrium that happens to be 243 days per rotation, the slowest planetary day in the solar system, slower than Venus's own year. Or perhaps no impact at all. Perhaps Venus started with a prograde rotation that was gradually, inexorably erased by tidal forces over billions of years. The slow retrograde establishment, not through violence, but through the patient arithmetic of gravitational torques accumulating over geological time. The honest answer is that we do not know which scenario is correct. We have physics that supports both. We have models that demonstrate both are possible. We do not have the specific measurements that would tell us which one happened. Those measurements are coming. Da Vinci will send a probe through Venus's atmosphere in the late 2020s, measuring the noble gas ratios that carry the chemical memory of whether Venus ever had liquid water, whether it lost an early atmosphere in a catastrophic impact, whether the volatile history of Venus is fundamentally different from Earth's. Envision will measure Venus's rotation with precision sufficient to determine whether the rotation rate is stable or still slowly evolving, still adjusting from some earlier state. Veritas will map the surface at higher resolution than Magellan, looking for the ancient geological record in the tesserae that might preserve evidence of what happened 4 billion years ago. The measurements will help. They will not resolve everything. The geological record has been overprinted by billions of years of volcanism and atmospheric processing, and some information is simply gone. But they will significantly constrain the possibilities. And whatever those measurements reveal, it will matter beyond Venus, because Venus and Earth started the same. They formed from the same materials in the same region of the same solar system, from the same gas cloud at approximately the same time. Their initial compositions were similar, their initial sizes were similar, their initial positions were similar. They were twins in the way that only planets in the same solar system can be twins. And they are utterly different now. Earth has oceans, Venus does not. Earth has a magnetic field, Venus does not. Earth has plate tectonics, Venus does not. Earth has life. Venus, as far as we know, does not. Earth rotates once every 24 hours in the same direction as every other planet. Venus rotates once every 243 days in the wrong direction. The rotation is not the cause of all of this divergence, but it is connected to it through the magnetic field that rapid rotation helps maintain, through the atmospheric circulation that rotation rate influences, through the climate stability that a magnetically shielded, moderate atmosphere enables. The rotation is one thread in a tightly woven fabric of planetary properties that together determine whether a world is habitable or hostile. Understanding why Venus spins backward is therefore not a narrow technical question about one planet's angular momentum. It is a question about the range of outcomes that planetary evolution can produce. It is a question about how likely it is that a planet similar to Earth in its initial conditions will follow Earth's path to oceans and life and a hospitable surface, versus Venus's path to a crushing, scalding, backward-spinning hell. In our galaxy there are hundreds of billions of stars. A significant fraction of them have rocky planets in their habitable zones, planets at distances where liquid water is, in principle, possible. These planets formed from the same raw materials under the same physical laws that govern the formation of Venus and Earth. Some of them are Earths, some of them are Venuses. The fraction that went one way versus the other depends on the specific processes that cause the divergence, including, possibly, the stochastic chance of whether a specific giant impact occurred at a specific time from a specific direction. If most Venus-like planets became Venuses, if the backward-spinning hellish outcome is common, then habitable Earth-like worlds are rarer than naive estimates suggest. If most Venus-like planets escaped the Venusian fate, if the backward-spinning outcome requires an unusually unlucky impact, then habitable worlds may be more common. Venus, blazing in the evening sky, is therefore a data point in one of the most important calculations humanity is currently attempting. How alone are we? How many other inhabited worlds exist? The answer depends partly on how commonly the Venus outcome occurs, and understanding the Venus outcome requires understanding why Venus spins backward. So look at it tonight, that bright white point of light moving slowly across the sky, never visible in the middle of the night because it orbits closer to the Sun than Earth does. Beneath that light, rotating right now while you watch, is a world spinning in the wrong direction, slowly, backward. 243 days per rotation, a day longer than a year. the sun rising in the west and setting in the east 116 days later. Something terrible happened to Venus long ago, or something patient and relentless happened to it over billions of years. We are not entirely sure which, but we are learning. The measurements are coming. The missions are being built. And somewhere in those measurements, in the noble gas ratios and the rotation rates and the surface maps, is the specific answer to why this particular world, this Earth-like world that started so similarly to our own, ended up the way it did, spinning backward in the wrong direction, for reasons we are still working to understand.